All right, so I want to finish up the material from Chapter 6, Section 6.3, which is known as solving a differential equation using the technique of separation of variables. So we teach a whole course at this institution on solving differential equations, and there's multitudes of techniques that we discuss in that class. The first of those is separation of variables, so it's a nice taste to see how that happens. So here's a differential equation on page 429, problem number 2. And just so you know, that dy dx business, remember that's another way to write y prime. So you may see either notation, but this notation is going to be more helpful to me today. Okay, so you may see all of that. I'm just going to put that in parentheses to the side. So using the technique of separation of variables is exactly that. I want to get all the y terms together and the dy's. I want to get all the x terms and the dx's together. So the solving is the same for all of them pretty much. But do you see how if I cross multiply, that's all my y terms, and if I cross multiply, that's all my x terms. So what I end up with is 3y squared dy equal to x squared plus 2 dx. And so what that allows me to do is now, once I have everything separated, now I can integrate both sides. And as always, any integration rule out there is fair game. Okay? So if I integrate over here, add 1 to the power and divide by the power is y cubed, technically plus a constant. We're going to handle those in a little bit different way in a moment. And then if I integrate on the other side, I end up with 1/3 x cubed plus 2x plus some other constant. I'll call those C1 and C2. It's nice, and I can't always do it in a convenient way, but it's nice if I can sort of kind of isolate the y term. I'm not going to take the cube root, but I am just going to get that by itself. So y cubed is equal to all of this, and then I'm going to combine those constants together. And this is where students' head sort of swims a little bit. This is a constant. It's positive, negative, 0. This is a constant. It's positive, negative, 0. I'm combining those constants together, and a constant plus or minus a constant is still a constant. So I'm probably not going to say C1, C2, and C3 anymore. I'm going to say a C plus a C is still some other constant. They're not all necessarily the same, but at any rate, there it is. And you remember in the last section, the last thing that we did was to use an initial condition to actually find the value of C. You do that in Cal 1 as well. It's just been a while since you've done that. Look at number 6 on that same page. Number 6 says x, y prime, all equal to y. So again, I'm going to rewrite that just so I can think about this separation of variables business as dy dx. So I sort of kind of have x's and dx's together. I think what I need to get rid of is the dy term. So I'll divide it away. The only problem now is I have a equation that looks like x over dx equal to y over dy. And we have no way to integrate that. So I do have a formula for that reciprocal. So you can do the math and the solving, but I'm going to flip over both sides of this equation. And as I flip it over, I like my y's on the left. So I'm going to rewrite this as dy over y equal to dx over x. And y'all, both of those now fit the form of du over u. So I can integrate. And so that integrates into the natural log of y plus a constant equal to the natural log of x plus a constant. And so I'm going to take a couple of liberties here. And again, we really need absolute value there, but to be honest, it kind of gets in my way, and I can get focused on that kind of stuff instead of the solving. So I'm going to rewrite this as the natural log of y equal to the natural log of x. And then I'm going to pull another sleight of hand. Right, this is some constant. I can write any constant as the natural log of some other constant. Why did I want to do that? Well, now I can make use of my properties of logarithms. If I'm adding, that's the same thing as multiplying. C times x. X times c. I just put the constant in front. And the whole reason I want to do that, y'all, is because now I actually can get rid of the natural log by raising everything to the power of e. So e and natural log, they undo each other. They're inverse operations. And e and natural log is still inverse operations. And so I get this for solution, which is a nice solution compared to those natural logs. All right, so again, separation of variables technique. Let's do a couple of problems, though, where we can come back and solve for this c. So look at number 14. Number 14 says the square root of x plus the square root of y, y prime, all equal to 0. And then they give us an initial condition over to the side. Sorry, all that's off the screen, isn't it? I apologize. An initial condition that says y at 1 is equal to 4. That's another way of saying whenever x is 1, y is 4 is what that means. So I'll use that to find c eventually. So I'm going to do like I did before, just to separate variables a little bit more efficiently. Maybe I'll make that y prime into a dy dx term. So again, let me subtract square root x from both sides. And since I've already got y's and dy's over here together, maybe I'll just multiply both sides by a dx term to cancel that out. So I'm left with the square root of y dy equal to negative square root x dx. And I'm almost ready to do the integration, but I think I'll go one more time and write it as a power. That makes the integration a little bit easier, and indeed I'm going to integrate both sides of that. So let's do it. Add 1 to the power and divide by the power. If I add 1 to the power, 1/2 plus 1 is 1/2 plus 2/2, which is y to the 3/2, and divide is 2/3, plus a constant's hanging out there. The same thing's going to happen on the other side, a negative 2/3 x to the 3/2. And then there is all the constants lumped together, plus c on the end. Okay, so normally that could be my solution to this problem. I tell you what, maybe I'll do one other thing here. Since there's a 2/3 there, maybe I'll divide everything by 2/3. That might make everything easier. So those go away. Those go away, but it's still negative. And then this, again, this kind of stuff drives students crazy. Y'all, it's a constant divided by 2/3, which, believe it or not, is still a constant. All right, if you're keeping up with them, they're all different constants, but we tend to just list it as a plus c each time. Okay, so that's a solution to this differential equation. It's a general solution. I now want to use my initial condition. So I'm going to let y be 4, and I'm going to let x be 1. And I'm going to use that to find a c. All right, so 4 to the 3/2 power, that's the same thing as 4 to the 1/2, and that thing cubed, which is the same thing as the square root of 4 cubed, which is 2 cubed, which is an 8. And 1 to the 3/2, I'm tempted to say 1 to any power is 1, and that's kind of sort of true. That causes us a few issues in Cal 3, but nonetheless, the square root of 1 is 1, cubed is still 1. This makes it be negative 1. And so if I add 1 to either side, finally I get that c is 9. So again, that's not a solution. That's just a piece of the actual solution. So the actual solution to this problem is y to the 3 halves equal to x to the 3 halves plus 9. So again, this was the general solution, and then this is a particular solution based on that initial condition. All right, so one other problem, number 16. Problem 16 says 2xy prime minus the natural log of x squared all equal to 0. So again, I want to use this technique. It's the only one I know, separation of variables. So I'm going to start by rewriting y prime as dy dx. And I guess I'll move the natural log to the other side. Might have to do some other moving, we'll see, but it becomes a positive natural log x squared. So it looks like, goodness, I need to get all my x terms together. This side has y's and dy's and x's and dx's. Maybe I'll move these two terms to the right-hand side. So I'm multiplying by 2x, so I need to divide by 2x. And I'm dividing by dx, so I'll multiply by dx. So notice pretty well everything on the left went away except for the dy term. And on the right, I'm left with natural log x squared over 2x times dx. All right, so let me see if I can't find some ways to work with that. This is going to be really more problem than I intended for it to be. If I use my properties of logs right here, I can rewrite that as 2 natural log x, right? Pulling that power out in front. And those 2's cancel out, so that's kind of nice. So integrating the right-hand side is the issue. So I am going to integrate both sides. I have canceled out the 2's. So I have the integral of dy. It's this piece that I'm not sure about, y'all. So it gets a little tricky here, and experience is a great teacher. If I write this as this problem, mathematically that's the same thing, right? If I multiply these two things together, I end up with natural log x over x. If I choose a u to be the natural log of x, then the du is u prime over u. So this is in the form u du. All of this became my du. All of this became my u. And again, you should have had a problem or two like that in your homework. It's just one of those kind of problems, to be honest. If I integrate dy, integrating one dy, that integrates into y. And if I integrate here, that's going to integrate into, find my other color, 1/2 u squared plus the constant. And again, I'm interested in not in u, but in 1/2 the natural log of x quantity squared plus the constant of integration. Okay. Still want to find c, and I didn't address the initial condition, but back in the original problem, we're told that y at 1 is equal to 2, which is another way of saying whenever x is 1, y is 2. So let me fill in those x's and y's into my answer, into my solution. So y is 2 whenever x is 1. And so you have to dig deep a little bit to evaluate this. The natural log of 1, remember that means, the natural log of 1 means e to some power is equal to 1, and the only power that can do that is the 0 power. So this whole thing is 0, which makes that whole term be 0. It looks like c is just a 2. So my particular solution here is 1/2 the natural log squared of x plus 2. You can verify that by taking derivatives and so on and substituting those things back into the original problem.